Greetings and welcome to a new video about the MOSFET amplifier frequency response. We will discuss the mid-band gain, the low cutoff frequency and the higher cutoff frequency in this example. We also discuss in great detail how we can extract the data from the MOSFET datasheet in this example in great detail. Of course, we'll see everything step by step in our calculations and verify these in SPICE simulations. And before we jump into the details, let's first discuss the outline briefly here for this video. Part 1 will discuss the MOSFET model parameters from the datasheet. So we will use the actual datasheet for MOSFET and use that to extract the model parameters. Now in part 2 we will do the DC analysis on our circuit. Part 3 will discuss the AC analysis specific for the mid-band voltage gain. Part 4, AC analysis for the low frequency cutoff, so the low cutoff frequency. And then part 5 will discuss the AC analysis for the high frequency cutoff, so the upper cutoff frequency region. Alright, so part 1 we discuss now the MOSFET model parameters from datasheet. Okay, now the MOSFET M1 is given here, which is the actual ALD1106, so you can find this on internet. And we will use a datasheet to determine the model of the MOSFET parameters for this situation. In this case, we will specifically discuss the threshold voltage, how we can determine that, the conduction parameter Kn, and also the channel length modulation lambda. Now this is the table from the datasheet of this ALD1106, a part of it. And you see here the important parameters for this MOSFET we will use in this example. Now first from the datasheet we see actually this first specification gate threshold voltage given here as the symbol VT, which is of course a symbol from the datasheet. And that is the threshold voltage. Actually it is specifically typically the 0.7, but it can be also minimum 0.4, but it can be also maximum 1. So the specifications are given here in some range. We will use the typical value of 0.7 here as our threshold voltage. And our symbol is here different than the symbol in the datasheet, so be careful about that. So VTH here, and they are using V capital letter sub T. Okay, the next one is about the on-drain current, which is the IDS on here. Again, their own symbol. Typically 4.8 milliamps, minimum 3 milliamps, but there is also a test condition where the VGS and VDS both are 5 volts. So we will write that down in our own way, in using our own symbol. So on-drain current, VD on, is 4.8 milliamps, and I take just to pick typical value, not the minimum. And I say also VGS is equal to VDS is 5 volts. This is the information we need in order to continue. The next one is about this part, which is the output conductance, given here as GOS. It is here given as typically value, no minimum, no maximum, 200 micro 1 over the ohms. That's the units of 1 over ohms, because it's the conductance. And again, the test conditions are given, VDS is 5 volts and the IDS, which is the drain current, 10 milliamps. So again, written in our form, output conductance G sub O, 200 micro Siemens, so it's the conductance, and for VDS 5 volts and drain current ID of 10 milliamps. The final one, which is important for our high frequency discussion, the frequency analysis, it's the input capacitance, last row. It is given as CISS, which is actually the input shorted form. With this, in this case, the capacitor here is 1 pico, typically can be 3 pico max. No test conditions are given. So I will write down as the input capacitance CISS is 1 picofarad. And this is an important parameter we will use later again in our high frequency analysis. Alright, now let's bring here, this is the part of the table we actually needed. So I just grabbed that one so we can now continue. So the threshold voltage, we start with that one. We already have it, so it is just 0.7 volts, so that's fast and easy. The channel length modulation, how we determine that? Well, this is the lambda we actually need. Now we know the RO is actually 1 over this GO, which is actually the output conductance. So this RO was our output impedance or output resistance in our model. We know that from our small signal analysis. And this is actually the inverse of that one. And we also know that RO itself is 1 over lambda plus VDS, which is our DC drain source current, source voltage, divided by the drain current ID. Now we need to know then how to rewrite this in a form that we can express now the lambda. In this case, you can see the output conductance is given for a specific VDS condition, also for a specific drain current ID condition. So we need to use that and also the value in order to calculate the lambda here, because that's the actual only unknown here. So let's do that. So ID times the 1 over GO is ID over GO is equal to this 1 over lambda plus VDS. That's actually shown here. And now I go a step further and do actually a couple of stuff at once. The lambda will be then expressed like so, where you see actually everything you can substitute from here, this part. And now we can say the ID, GO, and the VDS, and that will be substituted here. You can see that. And that will result in 1 over 45 volt inverse as the units. That's the exact value. And if you now type this in your calculator, you can hear 0.02222, approximately that value. Okay, that's our channel length modulation. Okay, how about the conductance parameter? That is actually the Kn. Well, our system or our MOSFET has the channel length modulation, so our current expression for the drain has this channel length modulation terms in it. So it is, if this was, for example, not there, then the lambda was 0, so there's no channel length modulation. Now we have it, so we need to include that. And this is only valid in the saturation region of operation of the MOSFET. We see here the Kn, we see here the VGS, we see here the threshold, we see here a lot of parameters. Now which one we do know now and which one we do not know. Now we actually know everything here except Kn. So let's look at the condition for the on-drain current, because that's the condition we need to know. Now I have really written this Kn, so I isolated that. So you see here ID over this complete part that's shown here. Do I know ID? Yes, because that's 4.8 milliamps. Do I know VGS? Yes, that's 5 volts. Do I know threshold voltage? Yes, that's 0.7. And do I also know the lambda? Yes, just calculate it. And do I also know the VDS? Yes, that's also here 5 volts. So I actually know everything here. So let's stop it here. You see that actually 0.0048, so it's 4.8 milliamps, 5 volts for the VGS, 0.7 for the threshold, lambda 1 over 45, and also the VDS is 5. Now if you do the calculation, you get here 233.64 microamps per square volt. This is an important parameter we need to use in our SPICE model we will develop shortly. Now the parasitic capacitances. Now well, that is determined from the input capacitance. Now you see here the MOSFET 2D picture. You see that in the inversion actually, because the channel has now this triangular shape. In the beginning it's actually shaped like this, like a rectangular, but now you get an inversion layer where you see this triangular shape. We see a couple of things here. We see actually the source, gate, and the drain on top, and we also have this bulk, which is also called the body or the substrate, which is given by the symbol B. There are a lot of stuff here, so let's go one by one. We have the VGS here, also VDS. That's actually together the CISS from the datasheet. Now there are also other parameters like the CDB, CSB, so I will not go into the detail of that. In this case, we primarily focus on the gate to source capacitor and the gate to drain capacitor. By the way, those are actually gate to oxide capacitor part of it, and now together they make actually the gate to source capacitor. So again, leaving the details out, this is called the gate to source capacitor and the gate to drain capacitor. Okay. Now we don't know actually what our individual values are. We only know their summation must be 1 picofarad as we have found from the datasheet. Now what we do know is, we can see here there's an approximation given in the literature that the VGS itself is 2/3 of the W, that's actually this width in the depth, times the L, the length of the channel, times the oxide capacity, which is actually the capacitor per square area, plus the overlap capacitor. And overlap capacitor is because of this overlap regions, because you see here this drain in the source will overlap in the oxide region. That's the effect of this oxide capacitor and the overlap capacitor. And VGD is itself is just this overlap capacitor. You can actually see that in the model. Now in this case we can say the overlap capacitor is then given by W overlap length, which is this the LOV, and the COX, that is the oxide capacitor here. And you can also do that same for the VGD, and the CGD. Now, we can now write down the following. So we can say the input short circuit capacitor CISS is given by this, but you can also use these expressions. Then you get here 2 times, of course, this, because that's the same thing. You have this now. Now we have a problem. As said before, no additional information is given to determine the individual values of VGS and VGD. So how do we continue? Well, one way proceed to look at it actually in the more practical way is to assume that the term of the oxide capacitor is dominant. That's also the case because this part of the oxide capacitor is much larger than the overlap capacitor. That's one thing. There's also another way to look at it. You can also say that the overlap length LOV is much smaller than the length of the total channel. That's actually another reason to say that the oxide capacitor is much larger. So if I look at this expression, you can see this part is probably much smaller than this part. So this part in total for the VGS is probably much larger than the VGD. So that's my conclusion actually here. So I say then we have the VGS, which is the gate to source parasitic capacitor, is much larger than the gate to drain parasitic capacitor. So together they must add up to 1 pico, but it can be that this is maybe 5 times, 10 times, maybe 100 times larger. We will now take just arbitrarily a value. In this case, I take the GS, so the capacitance between the gate to source parasitic capacitor, 9 times the gate to drain parasitic capacitor. Again, you can do also here 12 times, 16 times, because you don't have the necessary information, you don't know, but I will take that and use that in my model. What you should do, of course, in the practice, if you take this and you need to look at your results, you might need to change and adjust this, or you need to contact the supplier of this MOSFET and then get more detailed information if possible. So then we have the following. Since this is the ratio, so 1/9, that will be then the following. So 0.1 picofarads for the CGD, which is then the 1 femtofarads, and the CGS will be then 0.9 picofarads. So together again 1 picofarads. All right, let's continue now. Now we have the parameters here as we wanted. So we have the conduction parameter. In our symbol, there's an important part I would like to discuss here. So what we say as conduction parameter is different than what the SPICE says, because SPICE use Kp or beta in the simulators. The units are exact same, but this is actually 2 times what we actually mean by the Kn. So in our calculation, if this works, for example, 233.64 here, we should double this in the SPICE simulator. That's actually the meaning. Threshold voltage is exactly as we have it, so Vt is Vt, over the threshold. The channel length modulation lambda is just written out full, so lambda. This is the gate drain overlap capacitance per unit channel width. That's actually what you see here. So same for the gate to source, and the oxide capacitor is given as femto per square meter, so this different unit. So these are important parameters, looking at our model and looking at the SPICE symbol. Okay, let's bring them here. So these are the 4 parts we need: the threshold, channel length modulation, the conduction parameter, and the parasitic capacitors we have here. Okay, this is now the model, or the model we can build in our SPICE simulator. I call this the catalog editor in this case, and this is from the Tina TI SPICE simulator. You see here the simple model. This is the Schichman-Hodge model for the MOSFET, where you see the threshold, the beta, the lambda, the drain resistance, a lot of information here. So in this c00, the threshold voltage is just 700 milli, so exactly as we have it. The beta, as I said, should be then 2 times Kn, so that's actually 2 times this one, so that's actually shown here. So 467.28 micro amps per square volts. That is the reason for this. The lambda is 1/45, or 0.0222, or 22 point, a lot of 2's and the milli. Drain and the source resistance, which are the ohmic resistance, are 0, so there is no connections there considered. Gate drain capacitor, we have taken that as 100 femto, and the gate source capacitor is the 900 femto. These are these 2. Another parameter, we actually pick all of the 0 and then just this coefficient for the flicker noise as 1. All right. So we have now developed our model in the Tina TI SPICE using the information from the datasheet and also from the SPICE model parameters and our symbol. Okay, part 2 is about the DC analysis. So how do we do that? Let's now bring up our actual circuit we would like to discuss. So we see here the Common-Source Amplifier, the M1, which is our ALD1106, we extracted the following data: threshold voltage, the process parameter, the conduction parameter, and also the lambda. And we also know here the resistors, the VDD, which is our power supply for our circuit, and our capacitors C1, C2, and CS, and also load, which is 10 picofarads here. What we really like to know is the maximum voltage gain, the lower cutoff frequency, and the upper cutoff frequency for this circuit. So how do we work it out? Now, first we discuss, of course, with the DC analysis as said. So we go for the situation where we assume that the saturation region is valid. That means the following: the VGS, which is the gate to source DC voltage, must be larger than or equal to at least the threshold. That is the condition we assume. We will check this. And the VDS, which is then larger than or equal to this VGS minus the threshold. Again, we need to check both of them. Okay, this is now our DC circuit because the capacitor will be open, so you lose this part. Capacitor will be open, so you lose this part. Capacitor will be open, so you don't have this, so you have only this mid part, which is actually shown here. I also labeled here the G, which is the gate node, the drain, the source current, and the gate current. The gate current is 0 because this is actually functioning as a capacitor. For DC, it is open. You see the VGS and VDS. So how do we do that? Now, since there's no current in the gate, we can apply here at the gate node the voltage divider rule. And that is then shown here. So we have here the VG is R2 over R1 plus R2 times the VD. Now you substitute here the values: 400 kilo ohm, 600 kilo ohm, and also the 18 volts. You get here exactly 7.2 volts at this node with respect to ground. Okay, we can now apply the Kirchhoff's voltage law at the input loop. So actually this one. So you actually do here the loop. We say VG actually is equal to VGS. So this voltage is equal to VGS plus the voltage across RS. And since ID and IS are exact same, I just picked up here the ID. So that's now equation number 1. And again, as I said, ID is equal to IS, so I can replace that for this equation. And the drain current, since we are in the saturation region of operation and we have channeling modulation, we need to use this formula. We know the lambda, we know the threshold voltage, we know the Kn, so a lot of information is given here, so we can use that. Let's name this or designate it as equation number 2. So I will now substitute as equation number 2, this one, completely in here. So we get a larger expression. So Vg is equal to Vgs plus this expression where you see actually Vgs again as an unknown, but also another unknown, which is the Vds. So how do we tackle this problem? So we see here two unknowns, Vgs and Vds. Let's call this first equation number 3 and then continue. Well, the drain source voltage, which is this one, can be also written like so, because from here, from top to bottom, from the VDD node all the way to ground, I can say VDD is equal to RD voltage plus the VDS and plus the voltage across RS. Or you can say VDS is equal to VDD minus the RD plus RS together times the current, because they have the same current. So you can actually consider this as one branch. That's shown here. So this will help us to continue and calculate the next steps. So we can say the following: ID, which is actually our equation number 2, that can be now substituted in here. So you can actually see that. Again, you see here the VDS and also here the VDS, which now can do next is you can say now let's now work out the parentheses here. You can see VDD is now here outside, but you can also do 1 times this, which is actually shown here. And also lambda VDS times the exact same thing here, which is actually shown here. What I now will do is I will now bring this minus lambda VDS term to the left side. So I actually group all the VDS's. So VDS plus the lambda VDS, etc. is equal to VDD minus this term, which is actually shown here. Now why I do that? Again, to group the VDS terms, because I need to replace this in this equation number 3 because I have too much unknowns. Now let's do that. So I have here the VDS taking out of the parentheses, so it's just 1, and then lambda times this complete expression. Again, the VDS is taken out, and that is again the right side, which is not changed. And I can now do the following: VDS is equal to the right side divided by this coefficient, which is actually shown here. Now you see the VDS is expressed in all the parameters we know except the VGS. Now we can actually use this in equation number 3 to get an expression where you see only the VGS as unknown. So let's do that. First we have an expression where you see the numbers also, so the 18 for the volts. and this is together 1500, so what will be done 1500, Kn, etc. All the parameters are substituted, and that will result in this simplified form. And that can be then as equation number 4 substituted in as equation number 3. So we will do. So substitute equation number 4 into equation number 3. Then we have the following. Again, substituted also other parameters here. So we know the Vg, which is 7.2 volts. Rs is 500 times the Kn we have here, which is here. And we have also the 0.7 for the threshold. So everything is substituted. And also the VDS we just have. So also the 1/45 here because of the lambda. And we have now here an expression where you see the only unknown is VGS. So we can solve this. Now we can do it of course by hand, but you can also use a solver. So you can say to the solver, solve this for me, and then you have the following solution, 4.785 volts. This is larger than the 0.7 volts, so this is valid. So that is good, but we also need to check this VDS, etc. So how do we do that? Now we will do that in the next step. So we can say VGS is this, 4.785 volts, but we still need to check this condition, second condition, for the assumption of the saturation region. Now, before we jump to that, I will first also depict this way of solving in a graph. So you see here the red one, which is our 7.2 volts. So you see actually this is just a horizontal line. And this blue part of this graph is the left side of this equation, or this formula. You see here the intersection here actually. So at that moment, we see here the 4.785 volts, and that is also 7.2 as the Y value, and this is the VGS and the Y, the horizontal axis, and this is the value of actually these formulas or the expressions. So you see here in this case also as an intersection that the 4.785 volts is appearing. Okay, now let's also see if this VDS is larger than the VGS minus the threshold. So that's the condition. Again, our ID is equal to IS. So drain current can be also written like so, because we can say the Vg minus this voltage is the voltage across the Rs, because that is handy. And then we can now divide this by Rs, then we get the drain current. So first do that. Now 7.2 minus this, what we have determined, divide by 400, and you get here 4.82 milliamps. Okay. So drain source current can be now calculated, because we know the drain source current was given by VDD minus the summation of these two resistors times the drain current we just calculated. So we can do that, and that's shown here, and that will result in 10.76 volts. Is this now larger than the difference here? Well, VGS minus the threshold is 4.785 minus 0.7 is this, so 4.085 volts. And this is much larger than that one, so this is definitely okay. So we achieved actually our goal, and I actually have verified that the assumption was correct for this MOSFET, so we are in the saturation region. Okay, that's now for the DC analysis calculations. Now we do the simulation results here. You get here the simulation circuit. You see that some nodes, 4, 7, etc. and 1. So we will now look at this, and we also have the results from our calculations here in the slide. And you see also the table from the DC analysis. And what do we see? We have here the drain current. Actually, this is the current through the resistor RD from 0.2 to 0.6. That's actually shown here. It is actually 4.83 milliamps. So as we actually have calculated, so that's perfect. You also see here the voltage at node 1, which is 7.2 volts. So exactly as we have it, which is Vg. We also here have the voltage at node 3, so we can then do the voltage at node 1 minus the voltage at node 3 to calculate VGS. So that's actually what I will do. So VP1 minus VP3, so according to this notation from the table. If you now do the calculations, you get here 4.785 volts as we have, so that's nice. How about the VDS, because that's the voltage at node 6 and the voltage at node 3. Now voltage at node 6 is 13.17 volts. And now I can say, let's use this and also the voltage at node 3. Again, the same manner, that's VDS, and you can see that here. The value will be then 13.17 minus 2.415, and that will then 10.76 volt as we have. So this is nice. So we have verified our DC analysis in the simulations also. All right, that's now the part 3, which is the AC analysis for the midband voltage gain. And for that, we look at the small signal parameters first. Now we have the following. We have the transconductance, and we will also have the output resistance. Now the transconductance can be determined from the VGS versus the drain current expression, where you see actually here the threshold, because from the threshold on it will actually move up in the quadratic fashion, and this slope is what determines the GM, which is the transconductance. Now the drain current formula we have here in the general form, and the GM is then the partial derivative of this one at that moment, which is the VGS, which is the DC biasing condition and a DC drain current. So we will do the partial derivative of that one towards VGS, and we'll evaluate that at this capital VGS, which is our DC current, DC voltage. So we'll do that. So we will just do the derivative here, so 2 times the Kn, etc. And then you get, of course, also this term. And now we will evaluate this, so the VGS here, which is given here in the AC parameter, will be then the capacitor parameter. So this is our expression of the slope here. So GM is given by this. You can also write this in the form like so. So you can do V2 times Kn times the VGS minus V threshold squared. So you square this here, but you also need to do it down. So you get the exact same result. Why is this necessary? So you can see that this expression is actually this expression just 2 times here in the numerator. So you get 2 times the drain current divided by the VGS minus the threshold. This is just for convenience. And now we have an expression for the GM. Okay, that's nice. How about the output impedance? The output impedance, we look at the VDS, so drain to source voltage versus the drain current. And now you see here, it should be in the ideal case, this will look actually like a horizontal line, and for different values. So these are different values for the VGS. But we have a slope, and this slope is also the transconductance. I mean the conductance, not the transconductance. But it is 1 over the output impedance actually. So we need to actually look here at the slope. So 1 over the output impedance is what we need to find here. And that will determine, of course, by the lambda. So in this case, again, 1 over the RO is the partial derivative of this drain current expression towards, in this case, VDS, and we will evaluate it again, our specific VGS for our condition. Again, using that, so we just now differentiate towards the VDS, so actually this is all constants, so you see actually this, and you get down this result. If you now do 1 over this RO is then this, and the RO will be then 1 over this, that is actually shown here. So we can now use this also to determine the RO. In most cases, now let's say some cases, we also use for convenience 1 over the lambda ID, which is much faster because then you don't have to know this Kn and all the other parts, so it's much faster. Okay, so we will bring it here. So let's go to the GM and RO calculations. Now we can use the DC drain current and the DC gate to source voltage in here, and we can calculate the GM as shown here. So it is 2.365 millisiemens. In a similar way, we can calculate the RO here. We have the lambda, we have the Kn, and also the other parameters, and the result is 11.5 kilo approximately. Okay, so let's go now to the AC analysis for the voltage gain, because that's the objective for question A, and we know the GM and RO for our next steps. In this case, we assume that the coupling capacitors and the bypass capacitors are all shorted. So this is a short, perfect short. Load capacitor is open, so this is not there anymore. And the transistor parasitic capacitors like the the CGS and CGD are also perfectly open, so we don't consider this parasitic capacitor also. And then the circuit is like so. So we have this mid part, which is this, that's the model, where you see the GM VGS and also the RO because of this channeling modulation. And here we have the drain node, the gate node, and the source node. Now the source node, if I start with that one, that is shorted. Why? Because we have the capacitor CS, which is shorted because of this condition we use for this AC analysis for the voltage gain. We also see that this is shorted, and this RD is also going to VDD, which is in the AC domain grounded. That's why we also see this RD going to ground and RL also going to ground, so they are in parallel in this case. We also see this R1 in a similar form as RD going to VDD, but that's also AC ground, so it will then effectively come in parallel with R2. And we have here also a short because the C1 is gone. So we have now this simple small signal circuit where we can use to calculate the midband voltage gain. Let's designate here the VG, which is our gate voltage, which is actually exact same as VGS in this case. Now the voltage gain, which is our output voltage divided by the input, so VO over VI, can be divided in two parts. We can say that is VG over VI times VO over VG, which is exact same as VO over VI because you can divide out the VG here. Now this is more convenient to do in 2 steps, sometimes in 3 steps, depending on the complexity of the circuit, to go to the final result. So if I look here, I see a resistance of RG, which is the parallel combination of R1 and R2. Which is that actually very simple, in this case 240 kilo ohm, using the values of 600 and 400 kilo ohms. And this part, VG over VI, is simply RG over RI plus RG, which is a voltage divider rule, and that is actually this part. So I have now an expression for this part. So how about this VO over VG? Well, VO itself that's actually this voltage, which is then actually current flowing here, times the parallel combination of this, flowing here, times the parallel combination of these 3 resistors, so the RO, RD and RL. So we have here actually everything, times VGS, GM. Now GM VGS itself is of course in the opposite direction because it's going like so, and I will measure the voltage at this node towards ground, so I will have the current going like so. So I have to do the minus sign, that's the reason for this. So that means the VO and the VGS here divided by that, then we'll get a minus GM times the parallel combination of these 3 resistors. And this red one is now this one. Why? Because VGS is also VG. That's the reason. And then we have the following. So we can say the voltage gain total, VO over VI, is then the red times the blue one. So the blue one first times the red one, red expression. Now we know how we can calculate the parallel combination of the 3 resistors. We can actually see it here. So 1 over RD plus 1 over RL plus 1 over RO together to the power minus 1, which is also 1 over that. And that is actually shown here. So we get now here 704 ohms approximately for this part. Now GM we already know, 2.365 millisiemens. And now we can also substitute here the values for the RI and RG. And you get here a gain of approximately 1.665, which is 4.427 dBs. So it is inverted. In this case, it also has a gain, which is larger than 1. So no attenuation, and this is given in dBs. All right, that was that for the AC analysis for the voltage gain. Now we go for the AC analysis for the low frequency cutoff. In that case, we look at a different small signal model and small signal circuit for the low frequency cutoff. Now we will bring up all the capacitors back, so it's C1, C2, CS and CL, and we will consider this one by one. So in this case, where I will independent sources, I will disable them. So I have actually VI here as the only independent source. Load capacitor must be an open, and we also need to neglect the transistor parasitic capacitors, which are the CGD and the CGS. So they are all gone. Next, we will look at the situation by taking one capacitor at a time as we do it in the superposition. So we will take the effect of the C1 separately, C2 separately, and the CS separately, and we will then use that to get the final result. So we'll look at the contribution due to C1 only. How do we do that? Now we already have shorted this, so this is short. But we also need to short or disable all other capacitors. That means actually CS will be a short and C2 will be a short. So we will look at the between these 2 nodes, and we will make the CS a short, so you see the red wire, and also for the C2. And we will determine the impedance seen by the capacitor C1 only. So that's actually in this case, this part is RI. And looking here to the right, I see actually R1 and R2 in parallel. In this case, a time constant associated with this C1 is then given by the tau C1 is C1 times the impedance because of what the C1 sees. And that will be then C1 times Ri plus Rg, which is the parallel combination of R1 and R2. Now we already have this 240 kilo ohm. We all know what this is. So we can also use this C1 here, which is 1 microfarad. And that will result here in 10 to the power minus 6 times 100 plus 240 kilo ohms, and it was then 240.1 milliseconds. And the pole frequency associated with this capacitor C1 is the 1 over its time constant, and that's then given here, and it's then 4.165 radians per second. So this is a small value, probably not really dominant in our calculations, but this is what we have now for the contribution due to C1 only. All right, let's now look at the contribution because of C2. So we will leave actually these two again, and now we look at the contribution of C2 only. Now the C1 will be shorted, and we will look actually between the nodes of C2. The others are still shorted, so the input is shorted and the CS is shorted, and this is again an open load capacitor. So we will determine now the impedance seen by the C2. Now in this case I see that we have an RL here. We also see actually here this RD and the other parts here. So how do we determine that? Now let's first write it down in the general form. So tau C2 is then C2 times the impedance seen by this C2, which is Z sub C2. In this case we see here RD, and in series with that the parallel combination of RD and RO. You might say why? Well, this is ground shorted, so this RO and RD are effectively in parallel, and in series with that we have the RL here. So together we have actually this. You might say, is this GM is not having any effect? Well, since this is shorted, the current here is actually zero. So in total here, through these three resistors, we have zero current. That means at this node, we have the same potential, which is ground. And since this is also zero, so that means this potential is zero because of the shorted of the CS. VGS is zero. That means the GM times the VGS is zero. That means zero current. There will be an open circuit, so you can forget about that. That's the RO, and the RD in parallel again, effectively, plus the RL. That's actually shown here. And RO we know, that's from the calculation, RO and RD parallel, that's 920 ohms approximately. And then we have this value, which is 3000 plus the 920, and you get here 3.92 milliseconds, which in this case much smaller than that one. So probably this is also much dominant than the time constant because of Cu1 only. So the pole frequency associated with that one is now in this case calculated 255.1 radians per second. You see that actually it is much larger than the 4.165. Okay. Next part is about the CS, and that is the, let's say, the lengthiest word in this example. Because how do we do that? Now the contribution due to CS only, we need to look actually again between the two nodes. And we need to apply here, in this case, the test voltage and the test current method to determine the impedance seen here. So we need to determine the impedance seen by this capacitor CS by like so. So you look at it, and how to determine that? One way to do that is you can apply here a test voltage and a test current and do the ratio. Again, our time constant associated with that is similar to what we have done before. So the capacitor times its impedance. So what we do is we look here, so if we apply first a test voltage, I call this VT, and that will result in a test current, so the consequence of that one, and the ratio of that one is our ZCS. That's what we need to know. So this is just the Ohm's law, of course, but we can do that in any part of the circuit to determine the impedance at some node. Okay, this is what we need to use. So this circuit, that's actually what we need to use, and also the ratio VT and ID. We don't need to know the actual value of VT and ID, it's just a ratio. So we will apply a test voltage set and the source node, and then determine the impedance by using this ratio. Okay, so I call this small here, the branch here, I call this IX. It's also the same current here, which is also IX. And this current I'll call IRS, which is this current, which is not the source current, by the way, because the source current is a completely different thing. And then we have the following. So I can apply here at this node the Kirchhoff's current law. I can say IT and IX together will produce this IRS, but it's also equal to VT over RS, so I have actually used this. And I call this equation number 1. And I also say that this current through the resistor RO is IO. And I can say the IX here is then the GM-VGS plus this IO. You can actually see that. And again, the IX here and IX are exact same because this current will split in two parts and then come together. So this branch current and this branch current are exact same. Okay, let's again this node voltage as VD, that's the drain. And we have now the IX here, which is then also, if you look at it, because this is shorted, this is open, these two are the RD and RL, which are the parallel combinations. So that's actually RL prime. In this case, 750 ohms, combining the RD and RL. And this current here is actually going from ground up to the effective parallel combination. And if you now want to calculate the voltage at that node, you can say this resistor, RL prime, times the minus of Ix. That's actually shown here. So the Ix will be then minus the VD over the RL prime. Now the reason why I'm doing that is I will now have two expressions for Ix, and I can combine them and equate that together. I can say now the left side is this minus VD over RL prime is equal to GM VGS plus IO. I call this equation number 2, so I will use this. This is one of the important equations we have here. Now the IO itself, this current is also the VD, drain voltage, minus the test voltage divided by the RO. That's shown here, just again Ohm's law. And we have here equation number 3. Now we will substitute this equation number 3 in here, equation number 2. So we have this expression where you see the VD, the RL prime and the GM and other parameters. Now we will get in closer and closer because the final result should be only ID and VT. Okay, we also know that is also one of the important observations here. The VGS is actually minus VT. Why? Well, this is shorted. So in total, actually, you have here RI, R1, R2 in parallel. But since there is no current flow here because it's open, you can consider this node here, the gate node, as the ground. So there is no current flowing through this resistor. So that's 0 volts drop. So we can say this is ground. So we will actually apply the voltage here at the source part of the VGS expression. So it's actually the flipped version of the VT. So that's why we have the VGS minus VT. VGS is equal to minus VT. So I can replace actually the VG as by minus VT. That's what I can do. So that is another observation where we actually see another parameter is gone. So we see actually we're getting closer and closer. The only part is VD what we need to replace. Okay. I will now bring all the VD and all the VT terms together. So I have here VD over RO. I will place it to the left side. So you see actually that here. And of course everything is minus. So I will put the minus VD out. And also the VT terms. So minus VGM. So minus VGM. And also the minus RO. I will also put it in parentheses here and take the minus out. Now you see the expression of VD in terms of the other parameters we can use. So we can say divide out the minus signs and you do the GM. Let me go back here. So GM plus 1 over RO divided by this term. And that is times, of course, VD. I can also multiply the numerator and denominator by RO. That's then GM RO plus 1. And also do that here. So that I will get then RO over RL prime plus 1. That's actually shown here. And I can also multiply the RL prime for the numerator and denominator. And then I have this expression where you see this expression with no fractions at all in the format. Now this equation number 4 is not very useful. So we have the VD in terms of the resistors and the parameters we have found and also the V test. Now we will substitute this equation number 4 in the formula for Ix, which is this formula where you see the VD. So Ix is minus the VD over RL prime. Well, VD itself has RL prime in the numerator, so we will divide it out. That's actually effectively gone. And we have, of course, this minus sign. Okay, I will now designate this equation number 5. Then we can use this equation number 5, substitute it in equation number 1 here. Then we have the following. So IT, this Ix is here, so minus this complete thing with the VT in it. So that is perfect because that's the only thing we need, IT and VTs. And the right side is VT over RS. So you can see that we have an expression as we wanted, just in terms of IT and the VT. So test current and test voltage. Now we can now take the VT term here, so the right side, and then place it here together in a form. And then we have the ratio VT over IT. So there are a couple of steps here skipped. And now we have this expression. You see here directly the ratio we are actually looking for, which is now the impedance seen by the capacitor CS. So that is the expression where you see the impedance in terms of the GM, RO and the RL prime. So it is a quite complex expression. You cannot actually just determine that by looking at it, like what we have done for C1 and C2. So for the CS, you need to do more work. That's actually what you see here in more detail. Okay, now we'll bring it here and now calculate the pole frequency associated with that one. So then we have the following. So first the tau, the time constant. So it is actually this CS times the impedance. It's actually shown here. So all the parameters are substituted here for the GM, RO, etc. That will result in 2.3245 milliseconds. And GM was calculated already before, so if we now use also that and the G and the pole frequency, we can get the 430.2 radians per second for this one. All right. Now let's bring them all here and now summarize the contribution for the C1, C2, and CS. That's the C1, that's the C2, and that's the C3. Now what do we see? Well, this is probably not dominating, that's the smallest one. But these two are still not that far away. So 255 and 430. This is, well, let's say almost a double, maybe not double, but just larger than that one, but still not dominating. So we do not have a dominant pole. If this was, for example, let's say 4000, I should say, okay, this is dominating. So probably this will be our lower cutoff frequency. So in this case, there are several ways to find the actual, so to estimate the actual lower cutoff frequency, because the actual calculations are a little bit difficult and tedious. So we can do the following for our lower cutoff frequency. We can say, if we can dominant pole approximation, if of course it is not, then we can say the lower cutoff frequency is the largest omega p, which is the largest pole frequency. In this case, we cannot do that, so this will be not useful. We can do also the approximation, including the poles and the zeros. Now, we do not know the zeros, so you only have the poles. And that is given by this expression. Again, approximation is square root of the summation of all the poles squared each, and a minus 2 times the summation of all the zeros squared. So again, we do not the zeros, so this is also not at the moment very useful. We do know our poles, so all of the poles, and the approximation including only the poles is given by this. So this is just the summation of all the poles, so the 4.165, 255.1, etc. taken together will be then approximately here 690 radians per second. Now convert that into the hertz, you get now here almost 110 hertz. Well, this can be a little bit different in the actual simulation, non actual design in the measurements. Why? Because there are actually zeros here in the system, so we haven't taken that into account. So at least we have 3 zeros, because we have 3 poles, and 2 of them are at the origin, but 1 is not at the origin. But if you consider that also at the origin or very small, then the result will be a little bit different, and you can use actually this formula. So if you now assume that all the zeros are at the origin, then we have the following situation. So we can say, well, this is gone, so I will actually calculate my lower cutoff frequency using this formula without this second part minus 2 times the summation. Then we have the following. So you do now the square of the omega C1 plus the square of the omega C2 plus the square of the omega CS. So square this, square this, square this, add them up, and then take the square of that summation. And that will result in almost 400 radians per second, which is then approximately 80 hertz, so 79.6 hertz. It might be that this is much more closer to the simulations and the measurements than this one, again, because of the zero. All right, now let's continue with the part 5, final part in this video about the AC analysis for the high frequency cutoff. Okay, now we'll bring up now our MOSFET high frequency small signal circuit or small signal model in order to proceed with the question C, actually in this case. Now, this is the model we can use. It is the model where you see the lot of parameters, so the small signal parameters we see here, the RD, which is a zero bias drain ohmic resistance. This RS is the zero bias source ohmic resistance, sort of the resistance in these connections. And we have also the RO output resistance we have, of course, discussed before. We also see the CGD, which is the gate drain capacitor, which is our parasitic capacitor here, and also the CGS, which is our gate to source capacitor. And we have also this capacitor, which is called the drain to bulk or drain to substrate, that's B, which is the bulk. And we also have this other parameters like the GM and VGS. Now, normally what we do is we ignore RD, so we just say it is 0. We also ignore the RS. We also ignore this capacitor CDB. So we only have left this part here. So this is perfectly short going to the source node. So we also do not consider the bulk anymore because it's open. Normally it is of course connected internally in this discrete MOSFET. In this case we leave it out, and then we have the gate and the drain and the source here, and you see the 2 capacitors, parasitics, and 1 the output resistance RO. So this is now sufficient for our analysis, so we will use that for this circuit and also draw the other circuit parameters around that to determine the upper cutoff frequency F sub H. In this case, RO, GM, CGD, and CGS are shown here. Now you see here the small signal circuit as we have it. So you see here the actual model in the middle, and the R1 and R2 and RI, and also the RD, RL, etc. In this case, one thing is important: C1, C2, and the CS are all also shorted, so that's also what we have. CL it's not, because that will determine definitely the upper cutoff frequency. So that's why you see it in the picture. So how do we proceed in this case? Well, you can again apply the theory for the circuits and then come to the transfer function from the VO or VI. But we can use an approximation. First designate the gate nodes, drain, and the source node. Well, we can also use the approximation we call the Miller's approximation. It's not an exact, but it's an approximation which will allow us to do the calculations much faster. So how that goes is as follows. So we actually transform this circuit into a circuit where you have a capacitor here between the gate and the source, actually. You see that actually here, and also between the drain and the source. So we have two capacitors. The first one is called the CIM, which is the input Miller capacitor, and the second one is the output Miller capacitor. We will see how we can do that and calculate that in the next steps. So let's bring it here and do now the Miller approximation, and you see here the CIM and COM. First, the input Miller capacitors. The formula for that is shown here. So you see the feedback capacitor CGD will be reflected on the input, calling the input capacitor, Miller capacitor, given by this formula. So CGD times the 1 minus the voltage gain between the gate to drain. That's what's actually shown here. So how is that? Now that formula is actually minus GM times the parallel combination of these three resistors. That's actually shown here. So it's sort of the midband voltage gain, but then specifically for going to the gate, from the gate to the drain. Now that will be then substituted in here, so it will actually increase the gate to drain capacitor if you go this form. The output Miller capacitor is then given by this, so again CGD and then times 1, in this case 1 minus. Now next we will discuss how we can determine the time constants associated with the gate drain nodes. So for that, first we will short our input voltage, because that's the only independent source here. And we look now at the gate node, and for that we also need to look at the equivalent capacitor, which is the CGS plus the input Miller capacitor. And we will designate it like so. And together will be 900 femtofarads plus this 266.6 femtofarads, that will result in 1.167 picofarads. Equivalent resistance actually is the impedance or resistance between the two nodes of these capacitors. And that is the RI, R1 and R2 in parallel. That's as shown here. And together that can be calculated like so, and that is then in this case 990.96, almost 100 ohms. So actually this RI is dominating here. The time constant associated with this capacitor is then given by the tau G, which is then the equivalent capacitor at the gate node times the equivalent resistance at the gate node. The product of that one, so the 1.167 picofarads times this 99.96 ohms, will result in 0.1166 nanoseconds. Now next one, similar to the gate, we will do down for the drain. We will look at the equivalent capacitor. That is the COM, and in parallel to that is the CL, which is our load capacitor. Together they will actually make this equivalent capacitor here. That's now 10 picofarads plus 160 femto, so it's actually, this is dominating, so it together is 10.16 picofarads. Equivalent resistance seen at node D, which is actually the RO in parallel with RD in parallel with RL. And that's actually shown here, so that is then again, as we have calculated already, for 704 ohms. So together we can calculate now the time constant associated with this drain node. So tau D is then the equivalent capacitor at node D times the equivalent resistance at node D, and that is in this case 7.153 nanoseconds. So in this case you see this is the highest time constant, and probably this will also dominate the actual upper cutoff frequency. Okay, so the upper cutoff frequency can be calculated, it's an approximation again, using the 1 over the time constant associated with this upper cutoff frequency, and that is the summation of the time constant associated with this gate node, this one, plus the time constant of the drain node. So together they will add up to 7.27 nanoseconds. You see actually this closer to the largest one, because this is much larger than that one. And then 1 over that value will be then here 137.6 mega radians or million radians per second. If you convert that to hertz, that will give you here, divided by 2 pi, 21.9 megahertz approximately, or 21.89 megahertz. Now, that is what we have calculated for our upper cutoff frequency using this method, and this method is called the open circuit time constant method. For the high frequency analysis, you use the open circuit time constant method. For the lower cutoff frequencies, you use this short circuit time constant method. Okay, let's now look at our final part, which is the simulation result and using the Bode plot, where you see actually all the parts. So we'll bring up our Bode plot. You see here the gain and the frequency running from 1 hertz all the way to 1 gigahertz, and this is just the gain. And what do we see now? This is the circuit, of course, we have used. Now we have to calculate our midband voltage gain, or maximum gain, as minus 1.665. In dBs is 4.427 dBs, and you actually see that also here. It's the exact same, so that's a nice result. The lower cutoff frequency was in our case almost 110 hertz. That was the calculation we have done using the summation of all the poles. Now if you look at the result for the lower cutoff frequency, it is approximately 75.5 hertz. So this is quite off here, so there's of course an issue with the zeros, and we have of course discussed that, so I will come to that back to the later. And we have also here the upper cutoff frequency of 21.89 megahertz, and we have here 22.28 megahertz. So these are very close actually, so this is a nice result. And how about this lower cutoff frequency? Well, you can reason that to look at the zeros, because we have assumed that the zeros are not there, so we just made the simple approximation by adding all the poles. But if there are, of course, zeros, it will lower this value to maybe the actual lower cutoff frequency. Now, if we assume that all the zeros are 0, so that means at the origin, then we have the following value we actually have calculated using this expression. So it was 500 radians per second approximately, and if you now convert that, it will result in almost 79.6 hertz, which is much closer than that one. So in this case, we conclude that the zeros in this circuit are not negligible, so we need to add them. And our approximation for the lower cutoff frequency is in this case quite off. Well, you might say, how do we know that? If there's always afterwards? Yes, because the method we are using are based on short circuit time constant method and open circuit time constant method. Those are not exact methods, so they are using approximations, but it will allow us to move forward faster and then also see the picture which one is dominating and which one are not dominating. We have also seen that, for example, this omega C1 was the smallest one, and these two were dominating, so you can pinpoint which capacitor will actually dominate your lower cutoff frequency or the higher cutoff frequency. That's actually the advantage of using those methods instead of the exact analysis, where you see, of course, the complete and the actual expression, but it's of course not really intuitive and not design-oriented written. Alright, it was our example, the lengthy example about the frequency response of the common-source amplifier from the datasheet of the actual MOSFET, and we have extracted the data, and from there we have calculated our maximum gain, the lower and upper cutoff frequency, and we have verified this in the SPI simulations. If you have any questions, comments, please let me know. I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. There are more videos similar to this frequency analysis in the playlist shown in the video description of this video. So stay tuned and see you next time. Take care.